In this video we're going to look at factoring polynomials. Before we go through any of the procedures or ideas that we use to factor, what I want to do is I want to show you the purpose of factoring, its goal. We've already seen the standard form for polynomials, or the canonical form for a polynomial. If I write a polynomial in the variable x, I can write it out in terms of its canonical form as a bunch of different pieces all added together. And some of these pieces might be missing, some of these pieces might be negative, all of these things are possible. When we write out a polynomial in this form, it's easy to add it to other polynomials, it's easy to evaluate it, it's a straightforward computation to work with this for either polynomial addition, polynomial multiplication, or straight function evaluation. But what's hard about this form is to use it to find solutions or roots of polynomial equations. Oftentimes we're interested in knowing when a polynomial goes through the x-axis, when the value of a polynomial is equal to 0. Okay? And when we look at situations like this, these are called the roots of the polynomial. And it turns out that if a polynomial has a lot of roots, a factored form tells us what those roots are. It kind of gives us a picture of what the roots of the polynomial actually look like, what their values are. Okay? Now, let's do an example. And the example that I want to start with is just going to start out with a polynomial. And I'll write it in expanded form. And after I write it in expanded form, I'll show you the factored form and show you how easy it is to read off the roots from the factored form. So let's do a really simple example. Let's say polynomial x is equal to x squared minus 4. This is the example of a polynomial that I want to use. And when I look at this expression, suppose I want to know when is this thing equal to 0? What values of x are going to make this equal to 0? Now, this is a pretty simple example, and you might be able to figure out some of the solutions, but you might not see all of the solutions. Okay, so what I want to do is I want to show you the factored form of this polynomial, and then show you that that factored form actually gives us a concise way to figure out all the x's that set this thing equal to 0. So it turns out that this expression, x squared minus 4, can be cut into two smaller pieces. It can be cut into the pieces x minus 2 and x plus 2. And I'll show you that those are equal in just a second. I'll multiply it back together and you'll see that they're the same. But what I want to do is I want to show you how the roots can be extracted from this factored form. When you write down a polynomial in factored form, you have a bunch of pieces all linked together by multiplication. And this form is useful for finding roots of a polynomial because if you have a chain of things linked by multiplication and that chain is equal to 0, you can conclude that at least one of the things is exactly equal to 0, must be equal to 0. If you multiply a bunch of non-zero stuff together, you can't ever get to 0. So when you multiply things together and the final result is 0, one of the things that you put into the product must be 0. So when you factor a polynomial and you look for roots using the factored form, you're able to find the roots by taking each factor, each piece that's chained together in multiplication, and trying out, testing out what value of x will make that thing equal to 0. So this first factor would be 0 when x is equal to 2, and the second factor would be 0 when x is equal to negative 2. Right? Now, I made the claim that this is the same as this. So how is that true? That's true if we use polynomial multiplication to check that these two things are actually the same. So let's just double check that. If I want to multiply these factors out, I'm going to multiply the whole first polynomial by everything in the second polynomial. So I'm going to distribute the first polynomial across the second polynomial. So we get x minus 2 multiplied by x plus x minus 2 multiplied by 2. And now I'll use the distributive property again to spread this x across the first piece and spread the 2 across the second piece. So x times x gives us x squared. X times minus 2 gives us minus 2x. And from these second pieces, 2 times x gives us plus 2x. And 2 times minus 2 gives us minus 4. Okay? So when we combine like terms, we have an x squared by itself. We have a minus 2x and a plus 2x, and these two are going to cancel out. And then we have a minus 4. So these two pieces, when I multiply them together, give me x squared minus 4, which is the polynomial that we started with. The thing that's important to notice, though, is that when you looked at this first version of the polynomial, you might not have seen that both 2 and negative 2 are possible solutions. But when you factor it, each piece can be handled individually, breaking the problem down into simpler pieces so that you can find all the possible solutions. So our purpose in factoring is going to be able to take a polynomial in standard form and to try to break it down into component parts so that it's easier to find its roots. Okay? All right. Now, there are lots of different cases and lots of different situations that come up with factoring. And there are a few basic techniques that we want to look at. One of the parts of factoring that's difficult to master is the fact that it doesn't always work. It doesn't always work nicely, and it doesn't always work if a polynomial doesn't have any roots, it won't factor. Okay, so you have to be prepared to understand that factoring is a big mathematical concept, and you can't just break it down and turn into a single process. We have to look at different situations and different cases and then try and decide what to do in those specific situations. All right, now, what I like to do to start out here is to show you one situation where you might be able to factor, or to show you a pattern where factoring is guaranteed to work. And what we're going to do is we're going to look at a version of the situation that we just saw. We're going to see that x squared minus 4 is a special case of a pattern that factors really nicely. The pattern that I'm going to show you is called a difference of squares. And the squares here, they aren't shapes, they're squared numbers. Okay? So I'm going to show you the pattern. I'm going to use variables to represent the different pieces in the pattern. And then we're going to look at a bunch of different examples where this pattern pops up. Okay? So here's the basic pattern. If you have a difference of squares, the difference is a subtraction operation, and the two things that are subtracted have to be squares. Many times what you'll see is one variable and one squared number, but it's also possible to see two variables, which is what I'm going to use to represent the pattern in general. So if I have a difference of squares, the pattern in kind of standard form might look like x squared minus a squared. That's the pattern. Okay? A difference, and there are two squares. So it's a difference of two squares or a difference of squares. This pattern factors into two pieces. The two pieces that it factors into are the difference of the two numbers, x minus a, the two numbers are x and a, and x plus a. That always works, no matter what x is, no matter what a is. This whole thing is always equal to this whole thing. You can double check that using the same steps that I used in my first introductory example. I just distribute one polynomial into the other and continue to use the distributive property until I cancel all the like terms and get this version of this polynomial. Okay, so this pattern is called a difference of two squares. The x and the a are not really important. We could have two numbers or two different variables, and this pattern would still hold. This whole thing would be equal to this whole thing. All right, so let's look at a few different examples. Let's try x squared minus 1. That is a difference of two squares. I have the x squared, just like I did in the example of the pattern, and then I have 1. 1 is a perfect square. 1 times 1 is equal to 1. So 1 can play the role of a in this expression. If I want to factor this using this pattern, then what I should find is that we get x minus 1 and x plus 1. That's a factored version of the polynomial x squared minus 1. Okay. Another example would be 3 minus x squared. This one's a little bit trickier because I've put in the number 3. We don't usually think of 3 as being a perfect square. So in order to use this pattern, I have to think about this number in the right way. I actually need to introduce something to make it be a little bit messier so that I can think of it as being something squared. If I had 3 squared minus x squared, then the pattern would work perfectly, right? Because I could just say I have 3 minus x multiplied by 3 plus x. It doesn't matter whether I put the x first or second. It doesn't matter which one is subtracted, as long as the one that's subtracted changes sign in the two factors. So that's an instance of the basic pattern. But we were trying to look at a little bit more complicated example, which was just 3 minus x squared. So if we write that down, we need to be able to think of 3 as something squared. And the only way to do that is to kind of introduce a different way of thinking about 3 so that it can match up with this pattern. So we can think about this as the square root of 3 squared minus x squared. When we think about it like that, we have a difference of squares, and that expression factors in exactly the same way. The square root of 3 minus x, square root of 3 plus x. Okay? You can continue using the examples. You can have other things that come into play. You could have x's with coefficients on them and still use this pattern as long as you respect the structure as a whole. So another maybe a little more complicated example would be 9x squared minus 16. Okay? So I'm writing down this polynomial. It's a difference. I just need to think about it as two things that are squared in order to use this factoring pattern. So my first term, I can think about that as 3 times x squared. And my second term, 16, is a perfect square by itself. So I can think about that as 4 squared. As soon as I think about it as a difference of two squares, I can factor it using this pattern. And that gives me 3x minus 4 times 3x plus 4. So that's the difference of squares pattern. It's one option for factoring really pretty simple polynomials if they have that pattern, difference of two squares. We're going to look at one more simple pattern that comes up in factoring. And then we'll look at some other options in different videos. Okay, so the next pattern that I want to consider is called a perfect square. All right. And the perfect square is the type of shape, the type of polynomial that appears when you take one polynomial, usually a binomial, usually something that only has two terms in it, and you multiply it by itself. So here what I'm going to do is I'm going to show you the factored form first, and then I'll multiply it out into its canonical form. So if I have a perfect square looks like, say, x plus a squared. All right? X plus a squared. When I look at this pattern, the factors, I get two copies of the factor x plus a. So x plus a squared, by the definition of the exponent 2, the squaring 2, this has got to be equal to x plus a times x plus a. Right? And if I multiply this out, I'll use the distributive property, bring this first polynomial across each term in the second polynomial. So you get x plus a times x plus x plus a times a, and then distribute back, and we get x squared plus ax plus xa plus a squared. Right? And now if I use the commutative property and combine like terms, x plus a quantity squared has the standard form x squared plus 2ax plus a squared. Right? So if we're factoring, we would look for a pattern that has this shape and use the perfect square representation to factor it, to split it into x plus a times x plus a. Okay? So remember that when you're multiplying out, you go from a factored form to a standard form, but when you're factoring, you typically move from a standard form and bring that to its factored form, so you break it down into its factors. All right? So let's take these results and let's look at how we might use this for factoring. When we're looking for these types of patterns, they have to appear perfectly for us to be able to use these ideas. So if I'm going to find a perfect square, if I'm going to be able to factor something using this perfect square structure, I need to have an x squared, 2ax plus a squared. So these two parts of the formula have to match up, and there has to be an x squared somewhere. All right, so let me give you some examples where this works out perfectly, and then I'll show you situations where it doesn't actually happen, it doesn't pop out, which is one of the dangers of factoring, is that it doesn't always work, and it doesn't always work perfectly. So suppose we have x squared plus 4x plus 4. Okay. If this is a perfect square, it has to match up with this pattern exactly. I need to be able to choose one value for a that makes this part of the formula match up and this part of the formula match up. And they have to match up perfectly. Okay? So let's think about this for a minute. We need to pick a number a so that 2 times a is equal to positive 4 and a times a is equal to positive 4. We've got two conditions that need to be satisfied, but only one choice that we get to make. Right? So 2 times a has to be 4, and a squared has to also be 4. Those are the two conditions that need to happen. What number times 2 gives us 4? 2. So that condition has a unique solution. There's only one choice of a that will match up these middle terms. We also need to make sure, though, that the same a also matches up the last two terms. If it does, we have a perfect square. If there's any type of mismatch, then we don't have a perfect square. Okay? So if we choose a is equal to 2, 2 times 2 is equal to 4, and 2 times 2, or 2 squared, is also equal to 4. So this polynomial is a perfect square. It's a perfect square with x and a is equal to 2. So this piece, this whole polynomial, must factor into x plus 2 times x plus 2. And you can write that in terms of multiplication, or you could use exponent notation to write that. Okay? Let's do another example. try x squared minus 6x plus 9. Okay. We want to see if this is a perfect square or not. So we try to match it up with the pattern for a perfect square. We need 2a to be negative 6, and we need a squared to be positive 9. What times 2 gives us negative 6? Let's see. 2 times 3 is positive 6, so 2 times negative 3 would give us negative 6. So this first condition gives us a candidate for a, and then we need to make sure that it matches up with the third term, with the constant terms match up. So we choose a equals negative 3 to match up the middle terms. We have to verify and make sure negative 3 squared is equal to positive 9. That works. So this thing is a perfect square with x and negative 3 chosen for a. So this must factor into x minus 3 times x minus 3, or x minus 3 squared. Okay? We're going to do one more example. And this example is not going to be a perfect square. Okay? But it'll be an instance of something a little bit more general, which is called completing the square. So here's what I have in mind. X squared minus 2x plus, how about 2? Okay? If I'm trying to match this up with the pattern for a perfect square, we need the middle term to have the structure 2ax. And we need this last term to have the structure a squared. If we have x squared minus 2x, that gives us negative 1 as a candidate for a. We could choose a equals negative 1. But in this situation, a equals negative 1 does not match with this term. So this thing is not a perfect square as it stands. It doesn't factor as a whole thing. We can get around that in this situation, not by factoring it, but just by choosing a different representation for writing it down. Okay, so if I really wanted to try to factor out a perfect square here, the only way to do it is by what's called completing the square. And there, we group all the terms that make up our perfect square, and then we add a constant to that, or we leave off the part that doesn't quite fit. That allows us to do the factoring, but it has some leftover. There's some remainder that we can't get rid of. This turns out to be useful because it actually gives us a procedure that we can use to solve quadratic equations in general. So that's kind of a nice bonus. But this thing right here does not factor as a perfect square. It is not a perfect square. But we can write it out and still use these ideas to find a different representation, to write it in a different way. All right, so let's take the pieces, the x squared minus 2x. Those two pieces are part of what I want to turn into a perfect square. And if I chose negative 1 as my a from the second term, then I would want to add on to that an a squared. So I would want to add on negative 1 squared. Now, my problem, the actual polynomial that we started with, has a positive 2. So I can't just add in the term that I need without paying a price for that, or I'll change things. It'll alter the polynomial, it'll change it to be something completely different. So what we do when we're completing the square is we counteract the thing that we need. We introduce the thing that we want, the thing that will give us the pattern, and then we subtract exactly the same thing. Okay? And then this plus 2 term, we just leave that on the end. When we do this, then we can group some of the things together into the perfect square, writing out the factored version or the squared version, and then combining all the rest of the constants on the end. This doesn't help us find roots directly because we've got leftovers, but it can sometimes help you solve equations. It's not as easy as just factoring, but it still has its advantages. Okay? So these three pieces form a perfect square with a equals -1. So these become x minus 1 quantity squared. And then I can combine these constant terms. -1 squared is +1. So I get -1 plus 2 is +1. Okay? All right. So that's kind of the idea. So if you don't get a perfect square, sometimes that you can still find your way around the process. You can still force a perfect square pattern to appear, but it doesn't factor perfectly. There's going to be some leftovers. Right? So that completes this video, which is just an introduction to factoring, the difference of two squares pattern, and the perfect square pattern.